My guest today is David Siegel.
Great to see you again. You remember we spoke last year, and I gave a bit of a talk about the politics, and I promised some surprises in my next talk. And today I'm going to present some of my recent work on climate science. The more you study the climate system, the more complex you realize it is. I've spent a lot of time recently re-understanding the greenhouse effect, and I've realized that most of my previous videos weren't sufficiently accurate. In this presentation, I want to try to put the climate conversation in perspective. I'm always trying to be less wrong, not more right. So if anyone sees something I should correct, please leave comments and sources so I can learn more. Okay, in my view, there are two ways to think about the Earth's climate system: a radiative model or a thermal model. The radiative model looks at the energy balance between incoming shortwave radiation absorbed by the Earth and the long-wave infrared energy leaving. This is a popular but inaccurate model of the climate system. In the real world, energy coming in gets converted to heat, and that heat gets transported not just back up to space, but via four important gradients that we will explore. At the sun's core, two hydrogen atoms fuse into a helium atom, creating a huge amount of energy in the form of plasma, gamma rays, and high-energy photons. Once a photon is generated at the core of the sun, Tom, how long do you think it takes, on average, to make its way from the center of the sun, moving at the speed of light, to the surface?
Moving at the speed of light, not very long.
Well, it's a photon. But remember that the sun's core is very dense.
But it's still moving at the speed of light.
It's a photon. It's photon energy.
1 nanosecond.
1 nanosecond to get to the edge of the surface of the sun, where it can be then emitted and go out to space.
Sure.
Yeah, close, really close. 150,000 years.
Moving at the speed of light.
Moving at the
it's bouncing
speed of
all
light.
over the place.
Yeah, because it's blocked by everything else. It's super dense in there, and it takes thousands of years just to go a couple of meters. In fact, in reality, Tom, it's always getting annihilated and then re-radiated. It's energy, but if you think of it as the path of a single photon, it takes 150,000 years to get to the surface. And this is just solar science. It's just one of those wacky things that people don't know. So I thought I'd start with it. Mm. And then it finally gets to the edge or to the surface, and then it can go out to space. So 8 minutes later, some of those photons arrive on Earth. The sun is the size of a basketball, Tom. How big and how far away is the Earth? It's 100 feet away and smaller than a peppercorn, about the size of a sesame seed, 100 feet away. So we don't intercept that much of the sun's light. Mm-hmm. But it's about 170 petawatts of solar energy arriving to Earth at all times. About 30% of the photons that should hit the Earth's surface are scattered by clouds, land, and water and go back to space. What happens to those that hit the surface? Now, we're going to look at this two different ways. So the first is the radiative model, starting with the greenhouse effect. A high-energy shortwave photon comes in after its 8-minute journey from the sun. And when it hits an object, like a rock or anything, a highway, the high-energy photon is annihilated and heats the rock, which then radiates long-wave photons out according to its temperature. One short-wave photon generates about 20 long-wave photons on average, and they have much less energy. So let's follow one of those long-wave photons as it goes up. First, if that outgoing photon happens to be in the right wavelength of 10 to 14 microns, then it leaves to space unimpeded. About 12% of photons go straight to space that way, without adding to the temperature. Second, the photon can't hit an air molecule like nitrogen or oxygen and transfer its energy to the air molecule. That's impossible. These atmospheric molecules are transparent to infrared radiation. The photon can only interact with greenhouse molecules. So when the photon encounters a greenhouse gas molecule, and I'm going to use carbon dioxide as an example, this molecule absorbs the photon and begins to vibrate at a higher quantum energy state. Now, two things can happen. In the first possibility, that vibrating CO2 molecule could hit an air molecule and transfer its energy mechanically via collision. So the air molecule speeds up, increasing the air temperature. This is like a billiard ball hitting another billiard ball. The first ball comes to rest and transfers all its energy to the other ball. This mechanical transfer is called thermalization because the vibrational energy turns into velocity, which is temperature. In the second possibility, the CO2 molecule re-radiates a new long-wave photon out in some random direction and then goes back to its previous energy state. And that's the radiative model. Greenhouse gas molecules are constantly absorbing and re-radiating long-wave photons, so the energy makes a random walk up through the atmosphere to the top, similar to the way it did inside the sun, where it is finally emitted and goes to space. In this model, the atmosphere heats up because of the increased residence time of the photons, similar to putting on a sweater. In the radiative model, more greenhouse gas molecules absorb and re-radiate more energy, increasing the surface temperature. But that's not what really happens. In reality, the long-wave photon encounters a greenhouse gas molecule like CO2, and that raises the molecule's energy state, as I've said. But it takes on average around half a second before that greenhouse gas molecule re-radiates a photon away. Long before that, the CO molecule is struck by an air molecule and transfers its energy mechanically away. That's because air molecules are constantly bouncing off each other billions of times a second. So the collision almost always happens first, increasing the speed of the air molecules. The warmer air then rises by convection. At the top of the atmosphere, there are far fewer air molecules. At some point, an air molecule bumps into another greenhouse gas molecule that actually emits a photon and goes out to space. And this is how all 100% of the energy arriving on Earth eventually leaves to space through dethermalization via a greenhouse gas molecule at the top of the atmosphere. So CO2 does a huge amount of work ejecting thermal energy out to space. And that's not what really happens either. In reality, CO2 is a well-mixed gas. It's all up and down the air column. And they are emitting long-wave photons all the time. Some of these photons get radiated back down to the surface and start over. And this is the actual greenhouse effect. Because of pressure, moisture, clouds, latitude, and other factors, it's different in different places at different times. How much energy is transported by vibration and how much by radiation? Some people claim that radiation is most of it. Others claim it's zero. Well, rather than using theories and equations, let's look at the downwelling thermal radiation using real data from the Ceres satellites. Now, the poles are generally under clear skies. In July, the Ceres satellite instruments measure about 200 watts per meter of downwelling long radiation going to the Arctic surface. During those months, the North Pole receives sunlight all the time, so the atmosphere there has a mix of water vapor and CO2. They both produce downwelling radiation. They're both greenhouse gases. But during the darkness of January, there's still 100 watts per square meter of greenhouse effect. At that time, the air is very dry. It's extremely dry. So this is being done by CO2, not by water vapor. Think of it this way, Tom. If you look around at night with thermal imaging goggles, when you look up at the sky, you're not going to see black. You're going to see light because the goggles turn the downwelling infrared radiation into light. From this, we can see that during the summer, about 100 watts per square meter is from water vapor and another 100 from CO2. And we'll look at some other scenarios. In Antarctica, during the summer in January, you're seeing the inversion and the sunshine. Also during January, warm air is coming in from the tropics, and that mechanical energy sends more radiation down to the surface. Antarctica is the driest place on Earth, so almost all this radiation is from CO2. Now, why is the greenhouse effect lower in Antarctica than in the Arctic? Because Antarctica is that much colder and higher. Average elevation in Antarctica is about 8,200 feet. So there's less atmosphere in Antarctica and it's a bit colder. than in the Arctic. At sea level, these numbers would be higher. In the Sahara Desert, skies are usually clear and there's almost no water vapor, so CO2 is responsible for the overnight temperatures in the desert. At night in the Sahara, it's cold, but the air is much warmer than at the poles, which is why these numbers are higher than the polar numbers. I'm not going to translate watts per square meter into degrees because that's where all the fudging is. There are too many factors to do that with any accuracy. You can get those numbers all over the place. But here we see quite a lot of downwelling radiation at night from CO2, even under clear skies. Now in the rainforest, there's a smaller difference between day and night because water vapor is doing most of the work to keep temperatures high all the time. During the day, evaporation pumps most of the energy into clouds and up to the top of the atmosphere to escape. At night, the greenhouse effect is huge, but it's mostly done by water vapor. And this is under clear skies in the tropics. Now let's add clouds. Clouds reflect light away from Earth. They reflect heat down. They insulate, and they have their own internal radiative activity, not to mention electrical charges. So their clouds are far more complex. And I'm only showing nighttime data because that shows the greenhouse effect by itself. With clouds, there's more energy being re-radiated down to the surface. And that's why cloudy nights are generally warmer than clear nights. With clouds, water vapor does the vast majority of the work, while CO2 is probably around the same low level we see in the desert. But the Earth's surface is predominantly water, not land, so we have to understand what happens in the oceans. Wherever there's a lake or an ocean, there are two ways the incoming energy is absorbed. The first is right at the surface. A high-energy photon hits the surface of the water and evaporates water molecules, sending them up into the air. From there, the moist air expands and rises as convection moves the expanding air upward. As it gets higher and colder, water vapor condenses into droplets that form clouds. And that releases energy, which is then dethermalized by a CO2 or water molecule and sent upwards or off to space. There's no thermalization step at the beginning because it's just sunlight evaporating water from the surface. You don't need any greenhouse gas molecules to do that. The other scenario, though, is thermal. Sunlight is very strong. About half these high energy photons penetrate down tens of meters into the water. At some point, each photon strikes a water molecule, which heats the water directly, and the warmer water gets pumped around the globe to transfer its heat, and we'll talk about that in a minute. So these are nighttime figures for downwelling infrared radiation to the ocean's surface. It depends on temperature, air pressure, and moisture. But CO2 likely doesn't contribute much to the greenhouse effect on the oceans. Water vapor can do all the work here because water vapor and CO2 cover the same wavelengths. And since we know downwelling radiation can't penetrate the oceans, no amount of CO2 can heat the oceans. So let's just look at this for a sec. The oceans determine our climate, and the oceans, both warm and cold, have something like 330 watts per square meter of long-wave reflected radiation coming down to the surface. That's essentially the greenhouse effect, but is it from CO2 or water vapor? Over most of the ocean, it's almost all water vapor. But at the North Pole in darkness, there's hardly any water vapor. So I would say that tells me that most of this 100 watts per square meter here is a CO2 greenhouse effect, because there's no water to do that. So I think on average, worldwide, at sea level, about 100 watts per square meter of the greenhouse effect from CO2 really does exist. CO2 constantly feeds, and this is kind of the critical thing here. This is the crux. CO2 constantly feeds energy into the air column. It can absorb and transfer energy mechanically to the atmosphere millions of times per second while emitting a photon once every half second or so. So I would say CO2 is unsaturated. The same amount of CO2 can feed more energy into the air column if more energy comes in from the sun. More CO2 won't help feed more energy into the system because it only takes a handful of CO2 molecules to do the job. It's constantly feeding them in. Plus, in most cases, water vapor can do the same job, so CO2 is only necessary where it's very dry. So Javier Vinos calls this the pilot light of the climate system. It's been happening for billions of years, since there's always been at least 50 parts per million of CO2 in the atmosphere. Will Happer always says CO2 is saturated, which is why it has reached diminishing returns, but I'm using the word unsaturated to make the same case. I think we're technically saying the same thing. I believe CO2 can continue thermalizing arbitrary amounts of long-wave radiation because it has a huge capacity to do so. It's never saturated. By the way, Tom, when we talk about watts per square meter, we have to keep in mind that this is long wave, not short wave radiation. You can't compare long wave watts per square meter to incoming sunlight because long wave photons can't penetrate the oceans. It's a common mistake, but these numbers aren't comparable. So now, with the radiative model out of the way, let's turn our attention to a model that describes how the Earth's climate system actually works, the thermal model. So to do that, we need to focus on heat, not radiation. Heat always moves from hot to cold. That's what drives our Earth's climate system. We'll understand it using four temperature gradients, three of which we can see here. The first gradient is the vertical lapse rate. Almost all the heat in the atmosphere is down in the troposphere, which has the negative lapse rate we're familiar with. Most photons escape to space right below the tropopause, as we have just seen. The next gradient is the rotational gradient from day to night and back. The sun's energy comes from a single place, but it's distributed over a sphere, yet the radiation to space goes out at all angles. So remember that the greenhouse effect takes place in seconds. So if you just look at radiation, you'd say the Earth would be hottest at noon and coldest all night long when there's no incoming radiation. But that's not what happens. The surface and the air are hottest around 5 p.m., 5 or 6 p.m. We don't experience peak temperature at the time of peak radiation because the atmosphere and pressure systems build up heat during the afternoon and don't release it until after the sun begins to set. Again, this is driven by collisions far more than by absorption and re-radiation of photons. During an inversion or heat dome event, the radiation doesn't change, but the pressure does, and that changes the surface temperature significantly. This shows that the radiative model is wrong and the thermal model is a much better match. So now let's look at the meridional temperature gradient, which is the change in temperature from the tropics to the poles. We generally define the tropics as 30 degrees north and south of the equator, and the temperate zones from 30 to 60 degrees. The tropics cover half the surface of the area of the Earth, but this area absorbs 2/3 of the energy coming from the sun. This is because outside the tropics, the angle of the sun is spread over a larger distance, plus the sun's energy has to come through more atmosphere. The oceans absorb about 60 petawatts of energy daily and transport about 11 petawatts away from the tropics to the poles. This is about 20% of the energy coming into the tropics. Now, if we widen this area to 40 degrees, we have a net energy surplus from 40 degrees south to 40 degrees north. So more heat enters these latitudes than leaves to space. A significant amount of energy goes into the oceans and heats the water. That water first goes west because the Earth is turning east. And when that water gets to land, it turns toward the poles, north and south. From 40 to 60 degrees, the surface and atmosphere are roughly in equilibrium. This is the temperate zone where most of the weather is. The warm water interacts with cooler air and causes storms, hurricanes, and chaotic air movement that carries heat from the tropics to the polar regions. Beyond 60 degrees, more heat escapes the system than enters. The heat is transported to the poles about 2/3 via air currents and 1/3 via ocean currents. When ice melts during the summer, it's the climate system storing heat like a battery. When the polar summer ends, that heat is released as ice forms. It goes up through the polar vortex, completing the circuit from the equator to the poles and out to space. Now, if you use a local radiative model, you'd say the Arctic is heating up, and your scientists would tell journalists that they are very worried. But in a thermal context, melting ice is part of the annual conveyor belt, transporting excess heat from the tropics to the poles. It's been happening for about 14 million years since both poles froze over, as you'd learn in my class if you take it. About 20% of the energy coming into the oceans gets transported away from the tropics to the poles and then escapes through the polar vortices. Along the way, it converts between heat and infrared energy many times as it follows the temperature gradient from warm to cold. So these gradients drive the Earth's climate. And here's how we look at them. The temperature of the equator is in the center, and South Pole on the left, North Pole on the right. The planet is turned 90 degrees to match. During the Cretaceous, 100 million years ago, the temperature gradient was fairly flat. Most of the Earth was very warm. The continents were concentrated near the center, near the equator, and there were few storms. It wasn't as easy to move heat to the poles, so this Earth is very hot and very humid. This is snowball Earth, which may have occurred 750 million and 440 million years ago. Would have been caused by a combination of low eccentricity, the arrangement of the continents, and feedbacks. At its coldest, the temperature at the equator might have been below freezing, and there may have been some solid CO2 at the poles. That's also called dry ice, because the poles were so much colder than today. And look how extreme this gradient is. Look how sloped it is. The distance from the Earth to the sun, along with the shapes of the continents, gives us the meridional temperature gradient we have now, which is this blue line here. The average Earth temperature is about 14.3 degrees, and there's ice at the pole year-round, so we're in an ice age. And the shape of this curve determines the Earth's climate. This diagram from Javier Vinos's book shows the energy distribution by latitude. So the light blue dotted line represents the incoming energy from the sun, with the equator in the center and the South Pole to the left, North Pole to the right. Note the blocking of sunlight here at the equator due to clouds. That's this little dip here. There's a heat surplus inside the tropics of 40 degrees, as shown by the red area, and a net loss of heat at the poles, shown by the blue shaded areas. This data shows that the radiative model is invalid, and the climate system moves quite a bit of heat from the tropics to the poles. Now I'll build a simple but realistic energy budget. About 29% of incoming energy is reflected off clouds, land, and water back to space. That's the albedo we all know. About 3% is absorbed by ozone, and a full 20% is absorbed by the atmosphere. So that leaves 48% going to the surface. About 17% of that energy is absorbed by the land, and it makes its way back out to space via convection, conduction, and radiation, as we talked about. About 31%, twice as much energy, goes into the oceans. Half of that energy evaporates water and goes up to make clouds in the weather system. The other half penetrates and heats the water, and that heat gets transported poleward. So there's one final temperature gradient, and that's the thermocline going down into the oceans. The thermocline is largely driven by salinity, since saltier water is heavier. In the North Atlantic Ocean, the formation of ice sends tons of salty water down to the bottom of the ocean to return back south. Did you know, Tom, that all sea ice is essentially fresh water? Because you did. I didn't know that until, yeah, that's interesting. You can't really freeze salty water. Because of this sinking water dragged down by the saltiness, the Earth can be out of radiative balance as excess heat can go down into the oceans and stay there for hundreds of years. And it comes back out over decades or centuries as the gradients allow. And this is part of the global ocean conveyor belt, which connects 4 of the world's 5 oceans in a current that is driven by temperature and salinity. It takes a given water parcel about 1,000 years to complete its journey around the Earth. So sunlight can go into the ocean, and the heat can stay in the ocean for hundreds and hundreds of years before finally coming back out and going to space. You don't see that in the radiative model, but you do see it if you study pressure systems, ocean currents, and oscillation. So this is maybe the most important slide from Javier Vinos. Although his stuff is so good, I can't say which one is. It shows detrended data, which is just the relative ups and downs. And at the top is the Atlantic multi-decadal oscillation, a 65-year cycle that's just about to turn negative in a couple of years, 5-6 years from now. In the middle is the Pacific decadal oscillation, which you've learned a lot about, and which has a very strong correlation to temperature. This tells us that the ocean oscillations play a very important role in our climate system. So this is an assembly of most of the mainstream temperature series that try to show how CO2 is driving temperature, and it looks if you squint, it looks kind of hockey stick-ish. But even here, the fit with the AMO and the PDO is much better than with the CO2. You can see it goes up, it goes down, it goes up, it goes down, it goes up. It's flat a little bit. That's the pause, and then back up again. And this corresponds more to the solar cycle and ocean oscillations than it does to CO2. It's even more pronounced if you remove the urban stations that are heated by humans. Here, the blue dashed line shows data from rural stations that haven't been compromised. That line shows hotter temperatures in the past and milder temperatures in the last few decades. These are remote thermometers that haven't been encroached by civilization. And that's the opposite of the graphs you see on social media now. In both cases, there really isn't much correlation with CO2. It's because CO2 is not the driver. On the order of hundreds and thousands of years, temperature trends are mostly driven by sunspot cycles, which drive more or less energy into the oceans. There's a 2,500-year cycle called the Bray cycle and a 1,000-year cycle called the Eddy cycle. See how they both were at their minimum 400 years ago to cause the little ice age at the same time? And 2 more times before, it caused cold periods that ended many flourishing civilizations. We can predict from this sunspot model that the next double low point will be around the year 2450, when it may again be possible to ice skate on the Thames River, no matter how much CO2 is in the atmosphere. I'll give you 8 inconvenient questions for people who use the radiative model to explain how their model is the right one. The first question is, why is the Earth's temperature highest in July when the Earth is farthest from the sun, and it's coldest in January when the Earth is closest to the sun? A radiative model can't explain this, but a thermal model can, because the northern hemisphere has far more land to heat up as heat moves from the tropics to the North Pole, while the southern hemisphere has far more water, which absorbs heat and sends it directly to the South Pole. Land has a much larger influence on surface temperatures, which is what we measure, than oceans do, which is why the ocean temperature is always colder. And if you want to say that a certain country is heating up twice as fast as the world average, it's because of this effect. Next question, could something else be causing the warming of the last decade or so? Doubling CO2 would have a tiny effect on temperature, if any, but that's not true for clouds. Even a 1% reduction of cloud cover would have a significant effect on temperature. More clouds increase reflection and reduce temperatures. Fewer clouds means more direct sunlight hits the Earth, creating higher temperatures. Over the past 20 years, clouds have decreased, so more energy has entered the system, and we see a corresponding amount of energy leaving at the top of the atmosphere, which shows that heat isn't being trapped. There's just more energy coming in from the sun and going out. So question 3, what could possibly explain more heat escaping to space? The radiative model predicts that outgoing long-wave radiation will remain the same as heat builds up in the climate system from CO2, because the sun doesn't change, but CO2 does. But the thermal model accurately predicts more heat escaping to space as more heat enters, though with various time lags for heat transport. Question number 4. What caused the spike in temperature in 2023 and 2024? Was there a rush of increased CO2 suddenly? Or was it several factors working together? Decreased albedo, the positive phase of the AMO, a couple El Niños, the peak of solar cycle number 25, a change in ship fuel type that was started last summer, and a huge underwater volcano eruption. The volcano, which added 140 megatons of water vapor to the stratosphere, has increased the greenhouse effect in the stratosphere and has caused a lot of surface warming. But it'll dissipate over the next 5 to 10 years. And it may be radiative, but it isn't man-made. So question number 5, what's heating the oceans? The Argo float started measuring mid-level ocean temperatures 1,800 meters under the surface in 2004. Any ocean temperature from before 2004 is nonsense. Any numbers you see for ocean temperature before 2004 is garbage. And the result from the Argo floats is about 0.04 degrees per decade in less than 2 decades. Back radiation from CO2 can't warm the oceans. In fact, if anything, downwelling infrared radiation actually cools the oceans a bit through evaporation. The only thing that explains this rise in ocean heat is more direct sunlight penetrating the water. Fewer clouds, not more CO2, would do that. Number 6, why isn't Antarctica heating? Antarctica is the driest place on Earth, so the signal from CO2 should be very clean. Should be a one-to-one mapping. CO2 there is the same as everywhere else on Earth. You can see it in the background right here. The Vostok station is the coldest weather station in the world, but it only has data through 2012. I think it shut down, and it's too cold to go over there and do any upgrades. I'm not sure. As we can see at the Vostok station, temperatures are not moving with CO2. And this is the South Pole station where people actually live. They recorded their lowest ever surface temperature in 2021. This year, Antarctica had a sudden stratospheric warming. Event. The last one was in 2002. But those events have been happening for millions of years. They're rare, so people don't remember them, but like their more common counterparts in the Arctic, they're part of the natural cycle moving heat to the poles. That's because CO2 doesn't cause any warming at the poles. This graph is from a 2016 paper in Nature Climate Change showing proxy and satellite temperature data for the Antarctic. The red line is a proxy for temperature going back 200 years. And I want to read you that paper's conclusion. Climate model simulations that include anthropogenic forcing are not compatible with the observed trends. This suggests that natural variability overwhelms the forced response in the observations. The same is true in the tropics. Why aren't temperature in the tropics increasing? This is Pamban, India. From a thermal point of view, stable tropical temperatures make a lot of sense. If albedo is going down, you'd expect a slight rise over the last 20 years or so. That's basically what we see. This is Papua New Guinea. From a radiative point of view, we should see a hockey stick shape here, but we don't. That's because the tropics are insensitive to changes in CO2. Seychelles, Mahi Island, has data since 1890. And look, you can see about a 1 degree rise since 1980. That's from a remote weather station that they moved to the airport when they built it in 1972. So the weather people could more easily record the temperatures, more convenient to do it at the airport. So the story here is of stable temperatures followed by the growth of their tourism industry. That's what this graph shows. This isn't the thermal model. This is the data manipulation model, which is also very popular. If you only have the radiative model to work with, it looks like CO2 drives our climate. So here's a question, Tom. If water vapor is the main greenhouse gas, why doesn't the IPCC say we need to reduce water vapor? Why aren't there billions of dollars available for entrepreneurs to suck water out of the atmosphere? A lot easier than CO2. The answer, of course, is that it's not about climate. It never was about climate. I'm going to leave the questions here. There are a lot more on my website. If you use a radiative model, the Earth is going to cook over the next 200 years because there's no way humans are going to reduce their CO2 emissions. That's not going to happen. So let's look at some predictions for future temperatures. This is today. This is the last 100 years, and these are the next 200 years. And here, the IPCC prediction is the jagged red line. This is their new lower prediction, by the way, and produced by their models, which are programmed to be sensitive to CO2. This is CO2 level total cumulative in the blue. Now we know CO2 is going to continue to go up until nuclear power becomes mainstream, and it'll take hundreds of years to go back down. So the radiative people are sounding the alarm and selling solutions that undermine privacy, security, and the economy in exchange for authoritarian control. What a deal. But if you use a thermal model, you understand that solar variation drives the climate via oceans. Now, the black line is Javier's prediction here. On this time scale, he believes solar cycles will be the main driver of the temperature. And he thinks temperature will continue to rise for another 50 years, and then it will start to descend after the eddy cycle, that's the 1,000-year cycle, peaks later this century, right? About the end of the century, that will peak. Then it'll start to descend after the eddy cycle starts to go back down. Now, my prediction is just a little different, shown in red. I don't think it'll be as hot as Javier predicts. I think the AMO and the PDO are the biggest drivers. I think they have the biggest influence. The next AMO negative cycle, which starts pretty soon, will bring temperatures down or flat for 35 years. Then the radiative alarmists will have 3 decades of new records, heat waves, and fundraising. And then there's going to be a drop in solar radiation around years 2100 and 2200. That's the Feynman cycle. It's a cycle of cycles. But I believe ocean oscillations will continue to dominate. And these are just educated guesses. It'll turn out differently in reality. It'll turn out different in reality, but we can look forward to more plant growth for the rest of this century. So I've talked about 2 mental models for understanding climate. And it turns out you need both, the radiative and the thermal model, because they always work together. It depends on temperature, moisture, and air pressure, but there's always been at least 50 parts per million of CO2 to help keep the surface at sea level about 100 watts per meter warmer than it would be without CO2. And we need to study heat, and that's this small contribution here, but important. And we need to study heat transport via temperature gradients, since they drive the rest of our climate. And for that learning, I turn to 2 people who've helped me the most. Andy May, whose books and blogs are great examples of unbiased critical thinking. Many of us who are trying to figure these things out are flexible because many of our assumptions are wrong, and there's still a lot we don't know. The IPCC, with their settled science, is frozen in their views and will do anything to drive their political agenda. And Javier Vinos, who has taught me so much, and I'm glad to help others learn from him. Get Javier's books and read them. The one on the left is for people who want the big picture without all the details. The one on the right is master's degree level climate science. It's the textbook for my upcoming climate class, which starts in September. And I'm glad you asked about my class, Tom, because there will be a free webinar on Wednesday, September 11th and Thursday, September 12th. This webinar is not about climate science. There's no mention of climate science. It's about understanding the world through data and reason. And I'm not going to give too much away, but in this 2-hour session, I'll be giving 2 cognitive tests that will help you calibrate your critical thinking capability for any topic. You're going to need lined paper and a pencil or pen. The tests and evaluations will take about 90 minutes, maybe a bit more. Maximum number of attendees I can take for this webinar is 250 people. Anybody interested in critical thinking can take this. You don't need to take the climate class later. So there are 2 sessions that are free, and then the climate class will start a week later, beginning on September 18th and ends on November 20th. And the Thursday class starts September 19th and ends November 21st. The class is not for beginners. You should have at least 40 hours of independent study in climate science before taking this class. Everything takes place on a website where you can watch videos, meet other students, have discussions, ask questions, learn how to react to the latest crazy climate change, and more. There's also a mobile app if you prefer. All the lectures are pre-recorded. So I had 55 paying students last spring, and I did the lectures, and so they're already there. And those people will be there like my assistants to help answer people's questions. And then there's a weekly live session I'll host, and that's one for people in Europe on Wednesdays at 7 p.m. in the UK, and one for people in North America or around on Thursdays at 6 p.m. Eastern. So if you pay for one of those two, you can attend either or both. It doesn't matter. And you'll have access to the whole community. The live sessions will include some special guests. Last spring, we had Jim Steele, Nir Shaviv, and Chris Martz. We'll discuss what people are learning and what questions they have. So you can learn more. Sign up for the free webinar, although it's limited to 250 people per webinar, and register for the class at climatecurious.com. Hey, Tom, I really appreciate our conversation. I wanted to add one little thing. I've got my assistant Pickle here. And it's just that I don't really try or expect to convince anybody who's already decided that the Earth is dying, humans are destroying the Earth, and that giving money to the government is the only way to save the Earth. But there's one group of people I want to reach out to, and that's the lukewarmers. Now, I used to be a lukewarmer. I used to think that more CO2 would maybe make us a little bit warmer by the end of the century, and you may have been too, and many of your other viewers. And I think there are some prominent lukewarmers like Judy Curry, Steve Koonin, Alex Epstein, and even Will Happer and Dick Lindzen recently published a paper saying it will be some 0.001 degree more. This is in their report on temperature averted paper, and it's, I just don't think it makes any sense to talk about a dose response to CO2, no matter how small it is. And so when people like Steve Koonin say, well, it really doesn't make sense to go with renewables, so we should just continue to add CO2, this climate warming gas, to our atmosphere until nuclear can take over, and then it'll just naturally go back down. And then, don't have to worry about it because it'll be a little bit warmer, but that won't be too bad. It won't be terrible. But I just don't think it makes sense. I don't think physically it can happen. The Earth's climate system is going to do whatever it does, regardless of volcanoes or cosmic rays or whatever the inputs are, for example, that cause lower albedo. I don't know what it is, but we have no control over any of it. And so if I can accomplish one thing in my class and with my communication, it is that if you're a lukewarmer and you think there is some small dose response to adding CO2 to the climate, I think that you should revisit those assumptions and ask yourself what you're basing it on. So to be a member of the CO2 coalition, which you and I both are, you have to essentially sign up to say more CO2 would be better. And we all pretty much believe that. It would be better. And it has no effect on the climate. So the climate system will just do its thing regardless of anything we do. Even things we try to do to change the climate, I don't think have much chance of changing it. And we should just go about our merry way. There shouldn't be the word climate really anywhere except tourist brochures and maybe a few obscure academic journals. And the words climate and energy should never be used in the same document, let alone the same sentence. So I'm hoping that's my crusade. I think it's yours too, to tell people that, to help inform people to make a better decision, that lukewarmer is not really a category. And if you are a lukewarmer, come join us in the absolute denial camp, because we don't believe that CO2 has anything to do with temperature. And there's nothing humans can do to change that. Now, after all that, I'm sure you have hundreds of questions.
Yeah, excellent stuff. Great presentation. What other people have been influential in your thinking besides Andy May and Javier Vinos?
I look at a lot of papers. So I curate a list of, it's now 232 papers on my website. So I'm always reading papers. Obviously Dick Lindzen and Will Happer, bless him, he's tirelessly answers all my dumb questions. And you know what, Tom? I read about a paper, but I can't get it. And I email the author and say, will you send me this paper? I do that all the time. So authors around the world are sending me stuff, and I'm just kind of, accumulating from there. But I was taken by Don Shula's, is that his name?
Tom Shula.
Tom Shula, about the thermalization. And I don't know, what do I know? I don't know much, but I think he's kind of wrong that it's not all thermalization. I think I've just showed with data that it depends. It's complex. There's a lot of factors, but that there's always some amount of greenhouse effect going on from the greenhouse effect. So I guess a lot of the people that I've learned from are like when people make presentations on your podcast, I try to figure out if I agree, if they're right, if the data backs them up and so forth. So that's a lot of it. I'm so strongly influenced by Javier. I've read the fantastic book so many times, and I spend so much time with it that I'm just convinced that a lot of it is chaotic. A lot of it is not predictable. I mean, look at the La Nina and the neutral phases are kind of symbiotic. They go back and forth, but the El Niños happen when there's enough buildup of heat, and then it just trips a trigger and starts an El Nino, and that's why they're much more random. So how can you can't predict this? There's no cycle. I think there's a little too much cycling. The things that are clearly cyclic are orbital, obviously, and so the sunspots seem to be very, very cyclic. But near Shaviv and Svensmark came out with a paper saying that a lot of the albedo is controlled by cosmic rays, and that's like in the last 20 years. That's a cosmic ray effect that happens in decades, not millennia. So geez, it's kind of hard to it's hard to put cycles on all these things.
Do you have any thoughts on the role of volcanoes, whether somehow there's a predictable cycle in volcanoes or any other cycle?
I do. And that is the volcanic stuff has been happening forever. I'm not even sure that it's impacted by the Milankovitch cycles. Why would it be? I just think it's just plate tectonics doing their thing. And so whether they're influential or not is completely independent of everything else. And by the way, CNN, humans are not causing volcanic eruptions. It's like, I just think they just continue to do what they do, and whatever trends there are have to do with plate tectonic trends than anything else.
But possibly as the Earth is moving around, there are slight changes in gravitational pull, enough because the Earth's crust is so thin that is those slight changes are causing changes in volcanoes.
If you read the literature on earthquakes, mm-hmm. It's chaotic. It's, it builds up and up and up and up and up, and then it slips, right? Nobody can predict the slip. Mm-hmm. And the slip produces whatever we see and measure. Right? So it's like, there's this book about dropping grains of sand. I forget the book, but it drops grains of sand for a long, long time. And then all of a sudden something slips and the whole thing gives way and collapses. You can't predict that. So I don't know. I just think it's totally independent of practically everything.
Any other questions that I should have asked that I didn't? Or anything else you'd like to throw out here?
Well, I think that there are people who are predicting a Maunder minimum soon. I think Zarkova And some other people are sort of saying, watch out, the 21st century, there's going to be another Maunder minimum. That's a solar cycle. And I don't see how they can do that. Doesn't make sense to me. And so it just seems obvious to me that in 2450, there will be another minimum. You can pretty much, like clockwork, you can pretty much predict that because of the Bray cycle and the Eddy cycle coming together, right? Other things, other people, I look really critically at claims by people who present here and by people who write papers and people who, write on, what's up with that. For example, Jim Steele, I think, does a great job of showing how, pressure systems and local conditions create these anomalies that everybody gets all fired up about. And he's also big, and he and I talk a lot about downwelling radiation not being able to heat the oceans. There's some controversy about that. Roy Spencer says that downwelling radiation can heat the surface of the air above the ocean, and that can get mixed in, that warmer air can get mixed in and go down into the ocean. Well, he's a smart guy, so, okay, maybe, but how much? And also, if downwelling radiation is heating the surface, then that's going to cause a lot of evaporation, which cools. So I think it has to be net cooling. And this is a big deal because they talk about the oceans, heating up from CO2. And I think it's just another nail in the coffin in the radiative theory. I think it just cannot happen.
All right. And is it correct to say that, in your opinion, between now and 2400, we're probably going to see some slight warming and some slight cooling, but nothing super exciting necessarily?
It's so, the farther out you get, the fuzzier it is, yeah. Right? So, but look, 400 years ago, it was cold, and we've been coming out of that gradually. So the way Javier does it, and the way I agree with it, is you've got variation that is, what's the word? I forget the word. There's got variations that's going to happen anyway. So put that on top of the general trend, right? And then you're going to have peaks, and those peaks are going to set new records. It's like I say in the first Olympics, the first modern Olympics. How many new Olympics records were there?
All of them.
All of them. The next 4 years later, most of them went, and the next, you're going to get a lot of new world records all the time, both cold and hot. And so I think as long as we're on a trajectory up, there's going to be this continued sort of secular variation that people are going to cry about. And then as soon as it does turn the other way, then it's just, we're going to start going the other way. And it's pretty clear that I forget what I wrote. I've got a video on the long term, but I think it's within like 1,500 years, things are going to get a lot colder. And there was a mile of ice over Boston 20,000 years ago. And the only reason there won't be a mile of ice over Boston again in another 20,000 years, or I think it's 10 to 15, is if we figure out how to prevent it by putting a bubble over or superheating our cities, that ice is coming back. Okay. And if I remember correctly, Javier says that it's going to take a couple more of these obliquity cycles. The obliquity is responsible for most of the, within a 20,000, below eccentricity, the next one is obliquity. And these obliquity cycles aren't going to quite be as bad the next one, I think, but like in a couple of obliquity cycles, I think in 40,000 years, it's going to be really warm and nice. That's going to be a good time to have beachfront property. But in 1,500 years from now, it's going to be much colder. And it's going to get much colder from there. Humanity is going to have to figure this out. It's not for us, but it's for future generations. And it's likely to start in 500 to 700 years.
Okay, let's wrap up here then. Very interesting stuff. Thank you very much. And I put a bunch of your links into the show description. So climatecurious.com. You're at Pull News on Twitter.
Yes.
And yeah, so you can check the show description for those links. So thank you very much.
One last note about my class. It's just for personal informational purposes only. You'll never convince anyone who believes that CO2 is causing climate change that they, with science and data and rigor, that's not going to happen. But if you're personally interested, come take my class and enjoy the challenge.
All right. Thanks a lot for your work. We'll talk to you next time. David Siegel.